Module 9 Phase Diagrams, Part 3 Eutectic Phase Diagrams. In the eutectic system, within the liquid state, we do have two components here. For example, lead and tin are miscible, so they mix. But however, in a solid state, they are not miscible and they separate into two phases, alpha and beta. The separation occurs in such a way as to form a microconstituent called a eutectic, which is a very finely divided mixture of alpha and beta phases. And this actually enhances the mechanical properties of the material, resulting in increased strength. Also, we can see that the melting point of the eutectic composition, which occurs right here, is lower than the melting point of either lead or tin. So we've created a metal with a lower melting point by alloying. And this can be very useful for creating solders for joining metals. So let's have a look if we start off with a composition of melt that is actually too low for the eutectic reaction to occur. So in this case, we've got a 10% tin, lead tin alloy. As we cool down here, we start to hit the liquidus. And here we have some alpha forming within the liquid. And then at a certain point, it becomes single phase alpha. As we further cool, here, under equilibrium conditions, we should start to see some of the beta phase precipitate out into the alpha. And this occurs in the solid state, so it's a very slow reaction. Let's have a look at what happens if we cool a melt of the eutectic composition. As we cool, we have a liquid here, a composition, 61.9%, which is at the eutectic composition, right here. As we cool down, we see that we go from a liquid to a solid straight away. Okay, so this will solidify at a single temperature. There will not be a freezing range. And what will happen is that we will get lamellae of alpha and beta forming in the liquid, and when it freezes, we will have alternating lamellae of alpha and beta phases to form a eutectic. A eutectic is known as a microconstituent. A definition of a microconstituent is an element, or rather a component of the microstructure that has identifiable and characteristic structure. It may consist of more than one phase, such as with pearlite. So pearlite is a microconstituent of steels. In our case, our microconstituent is this eutectic. So you can see that below this temperature, we don't get a complete separation of the alpha and beta phases, but they occur as a finely divided lamellae. You can see this in the microstructure here. The lamellae form because the diffusion required for the elements to separate in this way is allowed to occur by diffusion over smaller distances. And we can see here the thermal arrest that occurs with a eutectic alloy. Even though it's not a pure material, it produces a thermal arrest at a constant temperature. And we can see why that is, because if we have a liquid of the eutectic composition, it will all freeze at one temperature. Here we have what's called a hypoeutectic alloy. Hypoeutectic means that the composition, in this case with respect to tin in the lead-tin system, is less than that required for, or less than that at the eutectic composition, which is right here. So when we have a hypoeutectic alloy in liquid state, we see we have a uniform liquid right there. Now we hit the liquidus right here. And within this state here, we're going to have liquid in equilibrium with alpha. The liquid will tend towards the eutectic composition. And when we hit this line here, the eutectic temperature, we're going to have alpha in equilibrium with liquid of the eutectic composition, and that remaining liquid will freeze as a eutectic. So we're going to end up with what is called primary alpha, the first phase to form during cooling in a matrix of eutectic. Now let's have a look if we have a hyper-eutectic alloy, which is where the tin or the component is the weight percent is higher than that for the eutectic composition. So in this case, we will see that the first phase to form now is beta. Okay, and as we further cool down, as we reach the eutectic temperature, we're going to have beta of 97.8% tin composition in equilibrium with the liquid at the eutectic composition. And once we cool down, what will happen is we will get beta in a matrix of eutectic. This is shown in this diagram here. Here we have the hypoeutectic composition. We have primary alpha in a matrix of eutectic. At the eutectic composition, we have all of it is eutectic. In a hyper-eutectic composition, the primary phase will be beta, and that will be in a eutectic matrix. So when we apply the phase rule to eutectic reactions, and we're interested in finding the amount of eutectic, we treat this as a microconstituent of the composition of the eutectic when we apply the lever rule. Let's demonstrate that by solving this problem. So we are given here for the lead tin alloy. Excuse me 1 second. Let me just make sure I have the focus. For the lead tin alloy of composition 80 weight percent tin, 20 weight percent lead. So let's draw that on our diagram. So we clearly have a hypoeutectic alloy. Determine the mass fractions of alpha and beta phases. Well, let me just read the rest of it. And at 180 degrees centigrade, do the following. Determine the mass fractions of alpha and beta phases. So in this case, once again, let's get a more accurate result by using the graph reader site. So I'm saving the image. You can do that by copying, pasting into Paint or Paintbrush. And then we can go to the graphreader.com. Opening my file. Just calibrating. Oh, that's the wrong file. And here we go. And then calibrating the scale like so. So I'm going from 0 to 400 on the y-axis and 0 to 100 on the x. Checking the result, so this should be, yep, 100, 400, and this should be at 0, 0. Very good. Just zooming in there. So the first question is at 800 degrees centigrade. So, 180, sorry, 180. So 180 is, I'm reading that y-axis is about here. Okay, we see that the eutectic is at a temperature is 183 degrees, so we're just under that. So for practical purposes, we can just read the values of the compositions from what's given in the phase diagram, because we're only 3 degrees below that. Okay, so we don't really need this the graph reader for this particular problem. So for A, we need to determine the mass fractions of alpha and beta phases. Okay, so we want the mass fractions, the total mass fractions. Okay, so even though the alpha and beta may be in the eutectic, we're not going to use that. Okay, so to do that, our intersection point is around there, and our tie line is across here, like so. So we have alpha of composition very close to 19% tin, and beta very close to composition 97.5. The average composition is 80%. So if I want the mass fraction of alpha, alpha's over here, so we need the length of this line. That is going to be 97.5 minus 80, which is what we will call the length of this lever, divided by the total length, which is 97.5 minus 19. Let's see what that gives us. (97.5) minus 80 divided by 97.5 minus 19. And that equals 22%. Now let's look at, to find the weight percent of beta, the easiest thing to do is we know that these two must add up to 100%. So we can do 100 minus 22, which is equal to 78%. Next thing is asking is determine the mass fractions of primary beta and eutectic microconstituents. In such case, the composition of our microconstituent is 61.9%. So what we want to use now, the tie line goes from the previous location on the right, but to the left. Let's call that B prime. That's going towards this is the distance between the nominal or the average composition and the composition of the microconstituent. So if we want primary, the weight percent of the primary beta, then what we need to do, we need to find the length of B prime, which is going to be 80 minus 61.9, and divide by the length of the tie line, but this time going from the phase boundary with B up to the composition of the microconstituent. So that is going to be 97.5 minus 61.9. Let's work that out. 80 minus 61.9. Divide that by 97.5 minus 61.9. And we get 51%. Now the remainder is going to be the eutectic. And the eutectic phase boundary is going to be here at the composition of the microconstituent. So we want to divide this length A by the total length of the tie line. That will of course give us 100 minus 51%, but just to show you that is true, that's going to be A over the length of the tie line here, which is 97.5 minus 61.9. A is going to equal 97.5 minus the average composition, which is 80, divided by 97.5 minus 61.9. Okay, which gives us 49% as we expected. Okay, now let's have a look at part C now. Determine the mass fraction of the eutectic B. So this is the beta phase that is within the eutectic. So we can see that the mass fraction of beta, this is the total, is going to equal the mass fraction of beta primary plus the mass fraction of beta in the eutectic. We're looking for this quantity here, so therefore mass fraction of beta in the eutectic is going to equal mass fraction beta total minus mass fraction beta primary. We calculated what the mass fraction beta total was over here. Okay, so these are the total values. Again, this is also total. That was 78%. We want to subtract from that the beta primary, which is 51%. And this gives us 78 minus 51 is 27%. So 27% of the beta mass fraction, in terms of 20% mass fraction of the sample is beta within the eutectic itself. So here we see an example of the application of the lever rule to a eutectic system where we're interested in the composition of the mass fractions of the microconstituent. Thank you.